And we now come to the second part of our session, which is giving the company sponsors of our conference a chance to tell you about their product. So please remain here. It's very important that they have the support from us that they deserve. And the first talk is going to be given by Adam Colin from RHK Technologies. And 15 minutes, please.
Well, thank you, Andreas. So my name is Adam Colin. I'm the founder and president of RHK Technology. So I'm going to give a little overview of the wide range of products that RHK has for the SPM community, some of the new things are in the works, and then a major change in the company. RHK has been in the surface science field since 1981. Our first product was a high-resolution electron energy loss spectrometer, followed by a temperature controller for temperature programmed absorption. In 1987, we introduced the world's first commercially available STM control system. And as the technology and the field requirements have advanced, we've continued to offer innovative new products, from our first UHV STM, AFM, our first digital control system. On our first control system, many people have seen the blue boxes. We've delivered over 1,000 of those. It was replaced by our R9, which is a digital system. In 2014, we introduced the world's first closed cycle STM system. So we've been building those systems now for more than a decade. We introduced our 10th generation controller a few years ago. That's something that has gotten wide acceptance due to its very high value proposition. In 2002, we introduced our PanScan Lumin, a system designed to measure light matter interaction with extremely high collection efficiency, where we can collect almost all the light coming out of the tip sample junction. And one thing that I'm proud to announce after all of these years, two of my kids, Ken and Ben, that have been working in the company for 15 to 20 years, have taken over, they're in the process of taking over ownership and management of RHK. So my tasks are being reduced, and now the second generation of RHK family is taking over. RHK is the oldest continuously owned independent company in the industry. We have three main product lines: our Beetle-based STM, our Pan, our cryogenic microscope, and then our control systems. The Beetle system is available as STM version, AFM. It's a cantilever-based AFM, so it allows you to do any non-contact mode as well as contact modes. That's something that's gotten to be much more prominent in the last couple of years. It's a variable temperature microscope. The microscope itself basically is at room temperature, but you can image the sample from about 25 Kelvin up to 1,000 Kelvin. These are used in a wide range of environments. Customers are using in ambient conditions, in liquid conditions. People like these because thermally they're incredibly stable due to the symmetric design. They have as low a thermal drift as many people's cryogenic microscopes, just sitting out in air. Electrochemical, this is a system here in Korea at Dr. Park that put in his own electrochemical cell. In the same lab, he also has one of our UHV AFM systems. With the system showing in the last talk, measurements made by Ron Neiman at Weizmann Institute is using an RHK microscope that we developed for him. He originally had a conductive AFM that would fit into a magnet from another company, but the thermal drift precluded making any real measurements. They bought our system, and it has more than 100 times less thermal drift than the previous microscope. Here's an example of working at elevated temperatures. You can see the sample really is glowing red hot. It's at 1,000 Kelvin. And it's still, you reach thermal equilibrium, it can still scan over the same feature with atomic resolution. There's a couple hundred Beetle microscopes around the world by many, many different groups. For the cantilever-based, one unique capability is the geometry of the optics, the laser, the cantilever, and the detector all scan together, so it acts like a sample scanning AFM. which decouples the normal lateral force, which is a real problem with when you're scanning a cantilever underneath the laser. So here's a group at the University of Michigan where they're measuring thermal flow through a single molecule, or a single atom. Terahertz-driven STM. Frank Hegman had bought this system. This is some very early work. They were very happy. It's been a workhorse for their group. They've recently bought a second system instead of UHV. They bought a high vacuum system, so we made the chamber for them much bigger with an optical breadboard inside, which allows them to bring, into the vacuum chamber, very close to the microscope, all the optics that he needs that were previously outside of the chamber. I'll switch over to the Pan style microscope. We call it Pan. It's in honor of Dr. Shu-Hung Pan that developed the amazing motor design that's used by most groups nowadays. For us, it's a whole family. The one scan head, we sell it individually. A lot of people build systems around it, put it in their own cryostat, replace homemade microscopes with it. But it can also be, we offer it just on a UHV flange. You could put it onto any available flange, on your chamber. That would be at room temperature with a flow cryostat, and then with our closed cycle cryostat. Here's an example of someone that took the microscope and put it into an existing Janus Millikan microscope that they already had. So it was really quite a simple matter. We actually just inverted it just to make the contacts easier. In the very beginning, everybody thought closed cycle would be a pretty good idea, except nobody thought it would work due to the high levels of vibration. So seeing is believing. So we took a complete system to many international conferences around the world, including one here in Korea. So the microscope is running in UHV at low temperature. Normally you'd move the noisy components, the chiller, the compressor away, but there's no room inside of a booth. So literally the compressor and the chiller were almost touching the microscope and still getting beautiful atomic resolution. Many people simply didn't believe it. They thought it was recorded data. So constantly during the show, people are reaching in and banging on the chamber to see if they can induce some noise spikes to prove it's really scanning. A nice feature with the way we developed this is the ability to have a very good optical access to the probe sample. You can get the glass to metal seal is here, so you're about 80 millimeters away from the lens to the tip sample, which allows you to locate features about 2 micron in size, which has been very important for the 2D material community. Here's some of the customers that have a closed cycle system. These are different versions, either just a head or the flow cryostat, so labs all over the world. The nice thing about a variable temperature system like this, it can work in any temperature. It's not just nitrogen, helium, or room temperature. You just punch into the temperature controller the temperature you want. In the drift, there's almost no drift at any temperature because the head, the probe, the sample, the body, and the inner shield are all at the same temperature. We're raising the temperature of the cold finger, so everything moves. There's no thermal gradients once it's reached equilibrium. Here's another example in Stefan Locke's group. Robert Reinecke, the person that did the work, is now here at the Institute working on their PanScan Freedom at the university here. A system we made for ETH Zurich. It was similar, except that they were putting it inside of a large electromagnet, not superconducting magnet. So this system, the microscope's in the UHV chamber, you change tip samples, and then it lowers down onto a manipulator where the chamber neck down and can go into the poles of their magnet, which can put about a Tesla infield, like on a little railroad track. They could rotate the magnet. Here's an example of one of the customers in Beijing. Here, they're on the 7th floor of their building, and they still get beautiful results. The system that I showed just before that, they're on the 4th floor of the building. So where many people that have, low temperature systems are in sort of nuclear bunkers, huge pits, vibration isolated. I don't think anybody with our system does that. This system's quite stable by itself. The latest thing is our PanScan Lumin, which is we developed in collaboration with one of our customers, the ability to collect almost all the light coming out of the tunnel junction. And the way this works is you retract the tip, and you can insert a parabolic mirror between the tip and sample, come back up inside through a hole. You can illuminate, focus the light on the tip, and you collect almost all the light coming out of the tunnel junction. So the only thing that's in vacuum, the only optics, is this one parabolic mirror, and then there's an in situ XYZ positioner to align it. So this is the XYZ positioner with the parabolic mirror. It inserts in, the tip comes in, you're ready to go. An important thing about having such a high collection efficiency, one, you can just go a whole lot faster. If sitting at every point, integrating data in a spectrometer can burn up a lot of time. But also you have to, without having this kind, you're going in with quite high laser power, which can bleach out your sample, damage the sample. So since you have such a high collection efficiency, you can really turn down the power of your laser. Also being reflective optics is very wide bandwidth. So you can work from UV to IR without having to change anything inside of the chamber. And the reflective optics are inherently cryogenic and UHV friendly. They don't outgas. You can bake them, which is not something that's the same. Putting transmissive optics into vacuum degrade over time. One new feature that we're putting on that one of our customers had requested, generally the first people wanted to scan really atomic scale, but if on some of the near field optics where you're scanning larger, scanning the sample, so we'll be able to scan the probe at high resolution and then the sample at plus or minus 15 micron at low temperature. Here's some of the results from the first Zaganel system. Another customer in Paris had one of our Beetle microscopes where they were collecting light coming off the back of the sample. It worked very well for them, but they wanted to go to low temperature. So like we do, we customize the system, we stretch the head, we put a Z manipulator holding a lens so you could focus the light from the back of the sample, then it's reflected out the side. So the customer bought the modified head from us, the controllers, and then they integrated it into their own cryostat. Our control systems, like I said, of our original designs, the analog boxes, we sold over 1,000. We've now sold several hundred of our digital systems. This is our 10th generation. It's really done very, very well for us because it's been really an amazingly good value proposition. Due to the modular design, you don't have to buy hardware or firmware that you don't need. So here's the box. All the A to Ds and D to As are on little plug-in boards. So you can, for a simple STM system, maybe you just need one A to D input. You can have up to 8 or 9 A to D inputs, lots and lots of DAC outputs. So some of the run at 1 megasample per second. Then we have a couple channels that are running at 100 megasamples per second, which for high-speed operations will give you 10 nanosecond time resolution on your measurements. So an example of that, we were running in Q+ mode, and it approached too fast and hit the surface, and you see a little spike in the force. Well, the data density is enough. You could zoom in on the spike, zoom in again, and you're seeing the individual oscillations of the tuning fork, where it whacks the sample, excites the second eigenmode, and you can see it as it decays. Another unique capability of the RHK controllers, everybody's control system stores the parameters you're operating. But if you change parameters during operation, it does not keep track of it. Well, the RHK system does. So every time you make a change, it puts a pointer into the file to the exact pixel location. So when you call up the image, you'll see exactly the point where you changed any of the parameters. Speed, feedback, bias, set point, that sort of thing. People use our controllers for homemade microscopes, RHK microscopes. We have a very large number of unicycle customers that have every generation of RHK controllers on them. Same with Omicron. Every model of Omicron microscope has multiple customers have RHK controllers on them. The R10 has enough hardware capabilities. You can run multiple sample or multiple probes, or actually 2 independent microscopes simultaneously. Here's an example of some of the people that have these. That's it. I appreciate everyone's time. We hope you'd consider RHK for your next project. The scan head, the pan head, and this Beetle head, I have at our booth if you want to come take a look at it. People are pretty surprised at how compact they are and the kind of capabilities. So thank you very much for your time.
Thank you very much, Adam. We have time for a quick question. Yes, Sebastian?
So thank you for the overview. For the applications with the light collection or light excitation, what's the biggest challenge in your mind for getting the optics to have high collection efficiency? What was the key challenge that you had to overcome to make it work?
Well, typically, if you're having a transmissive optics and you're some distance away, which you have to be, you're covering a very small percentage of the light that's coming out of the probe sample. So even if you come with something small, like a fiber where you can get close, you're still only capturing a very small part of it. Where here at the parabolic mirror, you're surrounding the whole probe sample. So the only part you're missing is stuff that's coming off almost parallel to the surface between where the mirror starts and the small hole where the tip is coming through.
I see. Thank you.
Okay, thank you very much, Adam. We move on to the second speaker. Just going to be, I don't know the name, unfortunately, sorry, but it's going to be given by Sienta Omicron.